Just a few hours north of St. Peter lies one of the most pristine wilderness areas in the country, the Boundary Waters Canoe Area. At night, there are no city lights, no house lights, no lights at all to obscure the dazzling complexity of the starry sky. The Milky Way stretches from horizon to horizon. Jupiter shines like a small moon. It is impossible not to wonder at the twinkling stardust, so infinitesimally small to our eyes, yet so incredibly stupendously distant. We see the universe at its limits on a still, dark night, a mystery, a riddle on the grandest scale. Frank Wilczek is a man well acquainted with the mysteries of the universe. As a child, he loved puzzles and games, so it was no surprise that he pursued a degree in mathematics at the University of Chicago, and subsequently graduate work in mathematics at Princeton. It was at Princeton that he learned of new work in theoretical physics that involved deep concepts from the mathematics of symmetry, in particular the gauge theory that was being used to describe electroweak interactions. He soon began work with a young professor named David Gross on the peculiar behaviors exhibited by subatomic objects called quarks. Quarks are the building blocks of protons and neutrons, thus of matter itself. Wilczek returned to the notion of gauge theory to model and thus explain the wild antics of quarks. For this work, he was awarded the Nobel Prize in 2004. Two things are immediately clear from even a brief review of Professor Wilczek's work. First, the sheer output of professional activity is truly stunning. Dr. Wilczek has published hundreds of research articles in a broad sweep of areas in modern physics. He has given invited talks at major universities and research institutions throughout the world. He has a rare gift for clear and engaging expository writing, with publications in Nature, The New Scientist, Physics Today, and Scientific American, as well as 3 popular books about physics. The second thing that is clear about Professor Wilczek's work is that it is infused with a sense of wonder about the world, a curiosity about what makes the universe tick. In his book, The Lightness of Being, he takes us on a journey from the Pythagoreans in ancient Greece with their motto that all is number, to the discovery of quarks and QCD, and finally to the frontiers of modern physics. It is a fascinating story. Professor Wilczek's playful and creative mind is evident throughout his career. In his book, Fantastic Realities, he describes how he came to predict the existence of a new particle called an axion. Axions might be the answer to the mystery of dark matter. When describing the origin of the name axion, Dr. Wilczek writes that, quote, "I named them after a laundry detergent since they clean up a problem with axial currents." Returning to the wilderness in our starry northern sky, we imagine all those throughout history who looked up in wonder and asked the question, what is it all about? This is the question at the heart of Frank Wilczek's work. It is my great honor and pleasure to introduce him today. Please join me in giving him a warm welcome.
It's lovely to be here, and lovely to have this cap to protect my hair-challenged skull from the sun. But we're enclosed here, so I can forgo that. Today, I'm going to talk about the universe at the limits of mind and matter, where mind meets matter in the subject of geometry. Geometry originated in very practical concerns. In fact, the word geometry derives literally from earth measure. But geometry took on a life of its own as people discovered it could be interesting, something you could play with, and that it led to very beautiful things. Perhaps the first great beautiful discovery in geometry was Pythagoras' theorem about the sums of the squares of the lengths of the two smaller sides of a triangle, right triangle, being equal to the square of the largest side, or hypotenuse. We don't know exactly how Pythagoras proved that, but it's very likely to be something like this. This proof, by the way, was the subject of a wonderful story by Aldous Huxley called Young Archimedes, where young Archimedes, this genius, Guido, discovers it. He's 9 years old or something, and draws the picture and says, "So simple." He sees Pythagoras' theorem in a glance, just looking at these figures. Let's spell it out a little bit if we're not quite young Archimedes. These two squares have the same size, and furthermore, they share in common 4 little colored right triangles. That means that if you take away the 4 right triangles, the areas of the remaining things have to be equal. But if we look at the left-hand side, we have the blue triangle, the blue square, whose area is the square of the shortest side of the triangle, and the red square, whose area is the square of the second shortest side. Whereas on the right-hand side, we have a square. When we take away the other with the triangles, we have a square whose area, whose side is equal to the longest side of the triangle, and therefore whose area is the square of the longest side. And so the 2 little squares have to add up to the big square, and that's Pythagoras' theorem. It's an unforgettable proof of an unforgettable theorem, and it appears in an unforgettable story, which I highly recommend to you. Pythagoras' theorem has inspired people over the millennia. In Einstein's autobiography, he mentions that his scientific awakening as a young man occurred, as a young boy really, occurred when he came to grips with Pythagoras' theorem. I remember that an uncle told me the Pythagorean theorem before the Holy Geometry booklet had come into my hands. After much effort, I succeeded in proving this theorem on the basis of the similarity of triangles. That's not really enough information to reconstruct Einstein's proof. We don't know what it is, but I've tried to reconstruct it, and in any case, I think what I'm about to show you is the best proof of Pythagoras' theorem, and makes it beautifully clear why it's the squares of the sides that appears. So here it comes. First, we have to make a preliminary observation about similar triangles. Right triangles, that is, triangles that have a right angle in them, will be similar. That is, there'll be magnifications or demagnifications, one of the other, if they have another angle in common. So if we have 2 similar triangles, and their sides are scaled up by some factor, one compared to the other, their areas will be scaled up by the square of that factor. Okay. Now in this diagram, we have 3 triangles. We have the 2 subtriangles and the big triangle. They all have an angle in common, namely phi, so they're all right triangles, so they're all similar. One of them has its longest side A. The other subtriangle has its longest side B. And the big triangle, the triangle made up of those two, has its longest side C. Their areas are proportional to the squares of the longest sides. So the areas of the two little ones have to add up to the area of the big one. And so a squared plus b squared equals c squared. Again, Pythagoras' theorem. I can understand, really, how constructing this proof might have been an inspiration for Einstein's entirely scientific career. It's so beautiful and such a wonderful thing to discover. Now I'm going to sort of give you a brief historical tour through the evolution of geometry and how it's enriched our concepts of the world and how it's changed over time. When you first learn geometry in high school, you may think that it's a static subject, that it's never changed, that the rules are forever. The philosopher Kant even elevated that to a principle, that the rules of geometry were inherent in the human mind and would never change. It's totally wrong, of course. The first era in the evolution of geometry, once the idea that you could prove things and that it was beautiful to play with figures, came when people tried to construct the world based on beautiful elements of geometry. And use geometry as a source of intellectual standardized parts that could be models for atoms or structures in the world. The most famous attempt, and the most profound and fruitful, was made by Plato and involved what are called the Platonic solids. So let me briefly introduce you to what the Platonic solids are. Let me start with something simpler, the regular polygons in 2 dimensions. So regular polygons in 2 dimensions would be polygons that have sides all equal and angles all equal. So the simplest example would be an equilateral triangle. But then you could have a bigger one, one with more sides, which would be a square, or a bigger one would be the design for a building in Washington, the Pentagon. And then you have stop signs and so forth. And you can obviously have regular polygons with an arbitrary number of sides. So there's an infinite family of these things. When we move to 3 dimensions, we get something much more interesting when we try to extend this idea of regular figures. If we ask for figures in 3 dimensions, all of whose faces are regular polygons, identical, and all of which come together at identical vertices, then it's a great theorem of geometry. It's the last theorem in Euclid's Elements, and widely thought to be what he was building up to in this 13-volume work, that there are exactly 5 regular solids. These are called the Platonic solids. There's the tetrahedron, which has 4 equilateral triangles as its faces. The icosahedron, a wonderful figure that has 20 equilateral triangles. The dodecahedron, which has 12 pentagons and is widely used as a calendar for that reason. The octahedron with 8 and the cube with 6 sides, used, of course, in conventional dice. Plato, inspired by the fact that there are a finite number of these things, thought that that should have a profound meaning for the structure of the universe. And notice that the number 5 is quite close to the number 4. And at that time, people thought it would take 4 elements to make the universe: earth, air, fire, and water. So Plato postulated that the atoms of these different elements had the different shapes associated with these solids. The tetrahedron, which is pointy, would sting when you touched it, so that could be fire. The icosahedron is pretty smooth. Different icosahedra will roll over each other nicely, so that's water. For some reason, octahedron's air. And Earth can be made out of cubes because cubes kind of pack and get stuck and kind of are earthy. Now, an ordinary thinker might have been discouraged by the fact that 4 is not almost, but not quite equal to 5. But Plato was a genius, and persistence is a big part of genius. So he was undaunted by this. He found a use for the dodecahedron. The dodecahedron was meant to be the shape of the universe as a whole, so it also had a role. Aristotle later, who always tried to one-up Plato, had a different theory. He imagined that the celestial regions outside of Earth, the so-called celestial spheres, had their own element, the so-called ether for the ethereal regions, and that the dodecahedra were actually the atoms of ether. Nowadays, it's difficult to agree with these theories in detail. However, the inspiration that symmetry determines the possible structures that we should use to describe the world, and that when there are only a finite number of them, that's suggestive of the classification of things that exist in the world, has turned out to be extremely fruitful, and in fact, the basis of modern attempts at unification in physics and chemistry. Plato was very good at getting his name attached to things, but he didn't actually invent the Platonic solids. At the Ashmolean Museum in Oxford, you can find these dice, which were discovered at a site in Scotland and dated to about 2000 BC, and which have the shapes associated with the different Platonic solids. So they're really in the nature of things, and people knew about it quite early, at least in operational terms, even if they didn't have theorems. These were undoubtedly used for some early form of Dungeons and Dragons. This kind of thinking of trying to match geometric structures, and in particular the Platonic solids, to the shape of the universe, really took its final and, I have to say, decadent form in Kepler, where he tried to fit the orbits of the different planets to circumscribed and inscribed Platonic solids, and thus determine the shape of the solar system. And it's a beautiful figure, but unfortunately has very little to do with reality. Because shortly after Kepler's work, and based on some of his detailed discoveries, a very different kind of approach to figuring out how the universe worked. Still geometric, but incorporating not the geometry of timeless perfection, but the geometry of things that change in time, took over. This was the profoundest aspect, I think, of Newton's revolution in physics. The idea that it's laws of change, laws, not static object, that are simple and fundamental. I think Newton first hit on this principle, not by watching an apple fall from a tree, but by thinking about something along the lines of this diagram, which is my favorite diagram in all the scientific literature, and is the first diagram in Newton's Principia. What is it? Well, you're asked to imagine someone standing on a mountain on a planet and on a body, could be Earth, and throwing a projectile horizontally harder and harder. And what would happen? Well, if you throw it not too hard, that's the familiar thing, it falls to the ground. But the harder you throw it, the further it'll go before it falls down. And Newton kept thinking harder and harder and harder, and came to the opinion, thought it was plausible or maybe even obvious, that if you threw it hard enough, you'd better duck because it'll come back and hit you in the head. It would never have fallen enough to hit the ground. So this concept means that the same thing, the same kind of force that causes things to fall to Earth could also be responsible for things orbiting. Furthermore, the mountain could have been bigger, so you could have bigger orbits. And for that matter, you could have other objects, not just Earth, but any object, having things falling into it or orbiting. So this suggests the universality of gravitation, that the terrestrial phenomena is the same as the phenomena that causes orbits, and that gravity is a universal force. Also suggests that orbiting is the same thing as falling. Just you're falling towards a target that's moving because you're moving, and therefore you never quite complete the process of falling. What's beautiful about this figure is not the shape of any particular orbit, but the thought that goes into it and the idea that the whole scheme of orbits makes sense and unites the idea of orbits and falling. Newton analyzed the motion mathematically as a series of small falls. So the object would move in a straight line if there were no force of gravity, but each time it tries to do that, there's a little force that deflects the orbital, the trajectory a little bit, and you can mathematically analyze the competition between those effects to determine the shape of the orbits mathematically. I think Newton, after considering the circular orbits, considered, suppose you threw it even harder, what shape would you get then? And that led him to the discovery of ellipses, which made contact with Kepler's work and drove the whole Newtonian revolution in classical and celestial mechanics. I really think it all comes from the visualization of that diagram that I showed you. And furthermore, the notion that motion can be analyzed most fruitfully from simplicities of its small bits, Newton generalized to a general mathematical framework for analyzing all kinds of things in terms of simplicities of their small bits. So for instance, to compute the area under this curve, you consider how fast the area is added to as you move along and add little bits to it, and you see that the area is going to be added to by the value of the elevation times how far you've moved, and that's the fundamental theorem of calculus from which so much flows. Newton's view of the world led to many triumphs and had an enormous impact on the surrounding culture, in many ways inspiring the Enlightenment. William Blake, in particular, was turned on by all this and imagined what Newton looked like as he was making his discoveries. I find this more or less plausible because I also like to work in the bathtub and looked very similar when I was discovering asymptotic freedom. that you can see in the determined look here and in the attention to detail that the new ethos of science also aspired to precision as well as to overarching ambition in describing the world as a whole. And Blake extrapolated that because this was the right way to understand the world, it probably was also the way the world was built. And I find the juxtaposition of these two figures quite remarkable. So I've discussed now how geometry suggested building blocks for the universe through symmetry, and how adding the time dimension really changed and enriched and made the picture more accurate. Now, the next big idea in expanding what geometry means is the idea that geometry is not the science of space as given, but a realm where you can imagine other things and make models that are unusual. So, and in particular, models where space is bent and curved. So, in particular, you can not only imagine a flat plane as the arena for geometry, but you can consider two-dimensional creatures who occupied a horse saddle like that, or who occupied the surface of a sphere. What would geometry be like for them? Well, they could have analogs of straight lines, the straightest possible path, the things that are locally the shortest distance between 2 points. But they would find, in the case of the saddle, that if you made a triangle, instead of the angles of a triangle adding up to 180 degrees, they always add up to something less. If you live on a sphere, they always add up to something more. And whereas on a flat plane, you can have exactly one line parallel to some other line through a given point. On the saddle, you can have infinitely many, and on the sphere, two lines always meet, in fact, in 2 points when you draw them, continue them indefinitely. So geometry expanded once we allowed space to become flexible. This idea was developed initially through the work of Gauss and Riemann, describing the geometry of a curved Earth and then extending it to many dimensional spaces, and brought to a new level when Einstein, combining these ideas about flexibility of space with the idea that geometry should also include time and the element of change, developed the idea of flexible space-time. So not only can space bend, but time can also bend and distort in response to physical perturbations, in particular to the influence of large bodies. So the ultimate example of this, perhaps, is the black hole. What I've shown here is, well, I'm not supposed to use that, sorry. Time runs vertically here, and you're supposed to imagine space running. Oh, this is fun. Space runs horizontally. So a curve like this represents the surface of a star moving through space as time passes and ending up in a collapse to a much smaller object. So this is a stellar collapse, and what happens, according to general relativity, to Einstein's theory, is that when that happens, the collapsing matter pulls along space and time so that these cones, which indicate the paths of light rays, the path that light would follow, and far away represent the speed of light. You go a certain distance as time travels, so you get 45-degree angle lines. Those things tip over, get distorted, and eventually you reach a situation where light can't escape. No matter how hard you try, the light cone has tipped over, so light moving into the future, instead of going off to infinity where you can see it, collapses like the matter into the singular point. Well, this is just one particularly dramatic example of the power and the strange things you start to encounter when you combine the idea of flexible space with the idea of combining space and time to have a flexible space-time. Another direction that's quite remarkable and has an unforgettable picture associated with it is that if you can bend space and time, you can start to blow bubbles, also known as creating universes. So this is a picture of a model of cosmology called eternal inflation, where universes, once in a while, sprout new universes, roughly speaking, new Big Bangs. And as time goes on, universes sprout universes that sprout universes, and you have this enriched picture, the multiverse, for what the ultimate reality of cosmology is. So that makes space very big in the sense of volume, and also very various in different directions. Now I'd like to add one more idea to the mix, the idea that not only can it be big in extent, but nowadays we have to consider that the universe is very, very rich in the sense of having many, many different possible directions. We're accustomed to thinking there are three kinds of directions, two horizontal directions, north, south, and east, west, and also vertical. So a three-dimensional space, and you can throw in one extra dimension of time if you want to add the dynamical element. But there's nothing conceptually to prevent you from thinking about larger dimensional spaces. You can even draw what a four-dimensional cube would look like. For a three-dimensional cube, the sides, the faces are squares. For a four-dimensional cube, the sides are cubes. And mathematically, it's not difficult to figure out the relationships that connect the different points and make a four-dimensional cube. Of course, you have to project it down to 2 dimensions to display it on a computer screen and apply considerable imagination to lift it up twice to 4 dimensions. But the information really is all there. What do these higher dimensional spaces help us describe? Well, many things, some of them are quite subtle and profound in quantum mechanics, but also the experienced world of a mantis shrimp. Human vision is sensitive to 3 averages of intensities of light from the electromagnetic spectrum. We have 3 so-called photoreceptors that respond, one mainly to blue light, one mainly to green light, and one mainly to red light. In reality, they all respond to a continuum, but with different efficiencies. And so, if you want to make a color photograph that humans will regard as being fully accurate, you only need 3 kinds of ink, because you only have to satisfy these 3 averages. Or if you want to make a computer display that has all the colors that human can sense, you only need 3 different types of light-generating elements. We say human visual space human color visual space is three-dimensional? Well, the mantis shrimp puts us to shame. It has 16 receptors. So its color world is 16-dimensional. Things that look the same to us could look very, very different to a mantis shrimp. It's capable of making much finer distinctions. It can also see considerably into the ultraviolet and even make distinctions among different kinds of ultraviolet light. So if you want to do justice to the visual world of a mantis shrimp, you need a 16-dimensional space to describe the intensity in all these different channels. Well, I can't allow the opportunity to pass to show you what this creature looks like, this genius of color space. And you see, even humans can see that it's quite colorful, and also that it has very, very strange eyes, kind of googly-eyed creature. But now we realize they're not only strange, but extraordinarily powerful and insightful eyes that in some ways put ours to shame. But we have one advantage over the mantis shrimp. We have a much bigger brain. And using our brain, we can imagine not only 16 receptors, but an infinite number of receptors. We realize through our brains that color space is actually infinite dimensional. There are any number of frequencies. There's a continuum, according to Maxwell's great discovery of the identity of light with electromagnetic radiation of different wavelengths. There's a continuum of different possibilities. We only see 3 averages. The mantis shrimp sees 16 averages, but our minds could allow us to imagine an infinite number. And in fact, we can even extrapolate and, using Maxwell's equations, bring in new phenomena that are not seen as visible light at all, and one wouldn't naively think had anything to do with light, such as radio waves, infrared radiation, ultraviolet, X-rays, and gamma rays. So nowadays, you also cook with it, not only see it, and listen to rock music with it. So now I'd like to introduce yet another idea from the expanding realm of geometry. This one is absolutely central to our best description of the physical world. It's the idea of something called internal space. This one is not very widely known outside of physics, and not very widely appreciated even within physics. So I'm hoping you'll help me popularize it. So we've discussed various complicated geometric objects. This one may look paltry by comparison, just a cylinder. Let me introduce, however, a little more structure to it, drawing a line. And now let me ask you to imagine that you are, or that you're imagining, creatures whose world is one-dimensional, that live on that line. Okay. And imagine that line is very long and they're pretty big, so that the cylinder seems quite small to them. And their eyes, their senses are incapable of resolving directly the structure in that second dimension, which looks like an extra dimension to them. What would things occupying different places in that extra dimension look like to creatures in this world? Well, they might look like different colors, but if they had different properties of other kinds, such as not the colors of the rainbow, but the colors we talk about in QCD, the colors of quarks, then what would happen is that you would see the same fundamental object in different places as being a different kind of particle. So instead of having many independent kinds of particles within modern physics, even within the Standard Model, and also in more elaborate forms in unified theories, we imagine, we postulate, and make successful use of the idea that many different kinds of particles can all be the same kind of particle, just in different places, seen in different places in extra dimensions. So as this particle moves around, if it's seen in different places, we don't sense those as different places in the normal sense, but as different particles. This is the profound idea that what you are derives from where you are. So I've described now several different ideas, I hope quite a few ideas, about the encounter between mind and matter, where mind has adapted geometry and changed it as a result of its confrontation with the realities of matter. Now I'd like to discuss very briefly the frontier of where mind and matter meet, and the distinction between them starts to become blurry. And I think where we're working towards a unified concept, where both mind and matter are part of this, are the same entity at some level, same deeper unifying entity. This wonderful object is an example of a fractal. I think any human artist who came up with this would have been regarded as an extraordinarily creative genius who dreamed up something essentially new and quite beautiful, just at the sensual level. But this is a mathematical object that's generated by the computer following very simple rules. I won't tell you exactly what the rules are, but trust me, they're so simple that even a computer can follow them. In fact, they're so simple that even a vegetable can follow them. You see, this also has this kind of broccoli, an extremely elaborate kind of structure that follows by iterating simple rules of growth over and over again to make this kind of fractal, self-similar structure. So simple rules can give complicated objects. And we have to expand geometry to allow the operation of simple rules of new kinds. This network is a representation of a piece of the internet, a rather small one, telling who's connected to who. And we're developing new kinds of geometry to describe these kinds of connections and networks. This is another network which superficially looks similar, but this is the kind of network you have inside your skull. This is the pattern of neurons that are connected to each other. You can see, if you look carefully, a few cell bodies, and it's actually much denser than this, but only some of the neurons get stained. There's not much empty space, but presumably it's wired up in a pretty structured way so that this thing actually does useful computations, such as taking input from the eyes, running through the network, and then being able to decide whether what you saw was Julia Roberts or this other person or a baby. Ideas of geometry and quantitative descriptions of the effects of one neuron on another and on the effect of the architecture of the network are a fascinating and very fruitful and fast-growing area of research. So nowadays, geometry has become very flexible, not only bringing in the time direction, not only bending space and time, not only allowing spaces of arbitrary dimension, but even changing the notion that it's the description of space in any very direct way. Now it describes relationships, but the same kind of mathematical techniques and rigorous approach are allowing us to understand also the neural networks and the social networks that are so important to humans. And so finally, the end of this story is that mind and matter are becoming united as mind, by studying matter, finally realizes what it actually is. Thank you.
Thank you, Professor Wilczek, for that fantastic lecture. At this time, I'd like to ask the rest of the panelists to join us up on stage here for the question and answer period. And as they come up, I'll remind people how we do the Q&A sessions here at Gustavus. The ushers will have small tablets for you to write questions on, pieces of paper, and you can submit them, write your question on them, and hand them back to the ushers. They'll bring them to the front where we'll collect them and get them to the moderator. If you're on the internet, you can submit questions by clicking on the Submit a Question. Make sure you submit the question for Lecture 1. And Google Moderator will help you sort those. You can vote for other questions that people have already submitted as well. And as we gather our panel up here, we'll begin the question and answer period very shortly. Thank you.
Sam Ting.
I heard he went to look for his wife, and they haven't seen him since.
Okay.
Very strange.
Well, they'll find him.
Steve,
Yes.
I'm John Young.
Hey, John.
We still have a couple more coming, or
So
But Ting is here?
Coyne is not in town yet. He's flying in as
Not?
we speak.
Okay.
Ting is here, but he apparently went out to look for his wife, and somebody's trying to find him. So we may just
go with,
move with what we've got.
we'll make it work, and if he shows up, we'll wire him up. If he
Okay.
walks up, we'll wire him up.
Great. Thanks, John. So, no, I'll in the moment when we open, I'll moderate. I'll ask if anybody on the panel has a question first, and give everybody here first shot, and then I'll have questions from the audience and questions from the internet, and we'll just we'll roll. And Frank can peer over my shoulder and see here's the questions that are coming in, right? The multiverse was the first question that came in. So. Yeah. Yeah, I mean, maybe Tom's with him. Yeah. Yeah, Tom's. And he missed the briefing at dinner last night, maybe, and doesn't know the routine. Could be.
I glanced occasionally just to check that people were seeing what I thought they were seeing. Pretty much. Because on my computer, you can see I have it.
Smile for Brianna.
Next, it has some timing information. But unfortunately, I didn't start my talk at time 0, so
Yeah, who knew?
I didn't know what. All right. Please.
All of when you're speaking with each other, you're going to hear your words coming from in front of you from these monitors, just to give you a little bit more presence, because it's so noisy in here, just so you know that that's where it's coming from. And you speak right into your mic.
Okay, straight ahead. That's Professor Ting. Excellent. Are you going to initiate this whole thing?
Yeah.
Okay. And you'll also do the when it's over. Thank you.
You set? Okay, please find your seats, folks. We'll get the question and answer period started in just a second here. Okay, Professor Mellema will start us off.
Okay. Thank you again, Professor Wilczek, for an amazing lecture. And I think we usually give our panelists the first shot at questions. So does anyone from the panel want to ask? Professor Krause.
So Frank, do you think ultimately geometry is everything?
Well, yes, because geometry, by definition, will be everything. All the concepts that are used to describe the world will ultimately want to visualize and play with the way we play with figures. So they'll become geometric, even if their origin wasn't anything we'd recognize as geometry today.
Thank you.
Professor Bates. Go ahead.
So, Frank, I was intrigued by the last part of your presentation in two ways. You talked about the notion of internal space.
Yes.
And then at the end, you drew this very strange figure with the U, and a number of us have seen that. One of the eye is sort of representing the operation of the mind. So are you one of these people who thinks that what the mind does, which is process data, has something to do with the universe, that is an idea that we're starting to see emerge in physics?
Well, first of all, I should say that that figure was stolen from John Archibald Wheeler,
I'm aware of that.
who loved to draw those kinds of
Yeah.
strange, profound figures. Well, some more profound than others. But well, I do think it may be a fruitful way to look for new laws of physics or understand implications of physical laws better, to think of them in unconventional ways now suggested by the study of neurobiology or by computer science, because it's given, just as in the early days it wasn't obvious that what geometers were doing measuring the Earth would turn out to be so fruitful for understanding the physical world, but they were doing a lot of stuff that you could exploit. Now, I think similarly, neurobiologists and computer scientists are developing ideas in information theory and analysis of networks that are very, very powerful ideas. And so we can look forward to stealing from them in physics. And also we can repay, because we have ideas in physics that I think can be very powerfully and fruitfully exploited in those realms and haven't yet been sufficiently appreciated. Yes.
Frank, when you developed quantum chromodynamics,
Yes.
was there much data upon which it was based?
Oh,
or
yeah.
was it largely mathematical, like string theory right now, and without that much
Well,
experimental grounding?
There were enormous amounts of data about how the strong interaction worked. And in fact, in many ways, the hardest part of discovering asymptotic freedom and realizing its importance was to separate the signal from the noise, because most of the data, most of this enormous accumulation of data about the strong interaction turned out to be, well, not wrong, but not central. I had a great advantage. As I was mentioned, I was only 21 years old at the time. I had the great advantage of not knowing very much. So I didn't know all this irrelevant stuff. And I was lucky enough to focus on just the stuff that led in the right direction. There were crucial experiments, in fact, pioneered especially by people at MIT. Kendall, Taylor was not at MIT.
Friedman.
And Friedman, of course, who's still very much with us and a good friend of mine at MIT. That showed some very unusual behavior of quarks, that when they're close together, they interact very weakly, although when they're far apart, they interact strongly. And also that when you hit them very hard, although they have very powerful interactions usually, and you would think that therefore if you hit them very hard, they would radiate a lot of stuff. In fact, they radiate very little. And it turned out that those were the right phenomena to focus on. And just by trying to understand those and make them consistent with general principles of quantum mechanics and special relativity, we were led to a unique theory. Now, the unique theory we were led to was a highly mathematical theory of symmetry. But it was definitely informed by very concrete experimental facts. And it wasn't long before Sam Ting and others did experiments that really started to give new kinds of confirmations of the theory. So it didn't go through this long period of being a promising theory that hasn't delivered, that some other theories we might mention have been going through.
Professor Shears has a question.
Yeah.
So Frank, I have a really simple question for you. So I'm an experimentalist, and I've heard many, many theorists talk about the beauty of symmetry and the beauty in geometry. What is that beauty for you? Is it the simplicity? Is it the compelling nature of the laws? What exactly?
Well, I like to quote Salieri here. In the movie Amadeus, Salieri looks at one of Mozart's compositions in the manuscript form and is in wonder at it, and says, if you changed a note, it would be diminished, and if you changed a phrase, the structure would fall to the ground. And that's a form of beauty. Everything fits. You can't change it without making it worse. And that's what symmetry in physical equations gives us. It gives us equations that can't be changed without making them worse, because their different parts have to be perfectly balanced so that when you make the transformations that the symmetry says you're allowed to make, you still get equations with the same content. So that mathematical idea leads you to unique, very structured equations. And then the miracle is that those equations are actually the ones chosen by nature. So it was the same instinct that led Plato to the Platonic solids as models of atoms, but this time it's right.
Other questions from the panel? Professor Smoot?
I'll try this a little differently, so you can rattle Frank this way. In fact, a lot of the recent history of physics, the last 40 or 50 years, has been about understanding symmetry and exploiting them, starting from Noether's theorem. And in fact, it seems to me people have pushed that to an extreme limit with supersymmetry, even though the data has not yet supported that theory, even it's quite beautiful. And just because it doesn't look like the real world, you have some spontaneous symmetry breaking or something to get out of it. But geometry has a lot of symmetry in it, but it's different. And I've been thinking for a while that people have exploited symmetry enough that they know it a lot better than I do, so I should think other ways. And I'm with you. I think geometry is a way of doing it. Geometry has some built-in symmetries, but it has some other factors. And so when you were giving this talk on geometry, I was so eager to hear what was going on. Are you thinking the same thing, that we need this new approach?
Well, in broad terms, I think you're touching on a theme that actually was implicit in my talk, which is that the original idea of geometry as a static perfection doesn't do justice to the possibilities. When you add dynamics, you get enriched possibilities. When you allow the structures to bend, you get enriched possibilities. So, and now when you consider networks and things that don't have a continuous structure, you get additional possibilities. So, so it's a balance. You have to, on the one hand, have a structure that gives you something to work with, building blocks, but then you have to be creative in using those building blocks, I guess. And a lot of, well, you alluded to this, but a big theme of physics in the last few decades is that symmetry can be very deeply hidden in the phenomena. You can have symmetry in the equations that doesn't show up in any very direct way in the phenomena. You have to look very, very hard to find it. But then, once you've found it, you can build back up to reality. So, physics as it's developed has come to use longer and longer chains of deduction, getting from the basic equations to the phenomena that you observe. I mean, it's famous, for instance, that in Newtonian gravity you can solve the two-body problem and get Kepler's law for planets. In general relativity, you can solve the one-body problem to get the Schwarzschild geometry. In quantum field theory, you can't even solve the equations for empty space. So, and yet that gives us the deepest description of the world. And So we have to use more and more chains of deduction between between the starting point and what we actually observe.
Other questions from the panel?
I have one more.
Mr. Gates?
Since implicit in the discussion of the last few minutes has been the notion of symmetry, I want to describe an experiment and get your response to it. One can take a human face and cut it in half,
Yes.
and throw away half of it and then invert and then glue back together to get an apparent human face back.
All right.
But people's reaction to that construct is actually very, very different than the original face.
Yes.
So do you think that this is some indication that we are so wired to regard symmetry as humans that it's a force in how we think about things far beyond the laws of nature?
Well, yeah, I think symmetry is certainly part of the notion of beauty, and is, well, of course, the way we use the word in science is somewhat different and more precise than it's used in general usage, but it's still the same word, and there's a reason for that. And symmetry in art and so forth has always been associated with the more general ideas of beauty. And well, as you said, humans are very attuned to symmetry or lack of symmetry, especially in other humans. I'm told, although I'm not an expert at this, I'm told that movie stars, for instance, typically have much more symmetric faces than the average human beings, because that is a sign of health and attractiveness that people use in assessing possible mates.
Let's turn to a question from our audience today. The questioner writes, regarding the theory on internal space, you said that different particles may actually be the same particle viewed at different angles.
Yes.
Should there not be an infinite spectrum of angles and therefore an infinite spectrum of particles?
Well, in classical mechanics there would be, but in quantum mechanics the infinity gets broken down to a finite number. So it's quantum mechanics that really enriches the picture and allows you to get a discrete number of possibilities out of a continuum of angles.
Another question from the audience. If time is the fourth dimension, can you speculate on how dimensions 5, 6, etc. would be described?
Well, I can certainly speculate. But I don't have to speculate. Even within this, within the standard model, I wasn't just making up this idea of internal dimensions. It's in accepted physics. It's the central concept in the standard model that, for instance, a quark, or a particle, a quark, in different directions in color space will be seen as either a red quark or a white quark or a blue quark, that we call them, will be seen as having different properties. And so that's what 3 extra dimensions look like. It's the dimensions that not all particles can move in. Quarks can move in those directions, but it turns out electrons can't, and that's why they don't participate in the strong interaction, theoretically. But we use very flexible ideas of what dimensions are in our equations. So they can look like almost anything.
Frank, I should add, though,
we use these extra dimensions as playgrounds for our equations. So you can use different equations based on those extra dimensions to describe a wide variety of things in principle.
But I should just add, in case people get a little confused by what you said, when you talked about red, we use the words color, but we don't mean color.
No,
we just
no.
ran out of words. Maybe not dimensions, but we ran out of words.
Well, it's a very unfortunate choice of words, actually, but Murray Gell-Mann chose it, and now we're stuck with it.
Yeah.
But when applied to quarks, the concept red, white, and blue really have absolutely nothing to do with visible colors. They're really different. They're much more like different kinds of charge, electric charge. But instead of, in electricity, we have just one kind of charge. It comes in positive and negative varieties, but it's just one. axis, so to speak. It's a strong interaction. It's kind of electrodynamics on steroids, and we have three different kinds of charges. And they're called colors for historical reasons.
I'll turn now
Basically because Murray likes to be clever. You know.
Let me turn to a question that came via the internet today from Alex in Sheboygan, Wisconsin. He asks, can we discuss multiverse theory and its relationship to geometry in some more detail?
Okay. There are actually two important multiverse theories in contemporary physics. One of which I think is, well, even it is controversial, but I think it deserves not to be controversial, having to do with quantum mechanics, where the wave functions that we use in quantum mechanics describe many, many possible outcomes of experiments that don't occur. When we make a measurement, we find out one result occurs out of many possibilities with different probabilities. And a possible interpretation of that, called the many worlds interpretation, which I really think is the only consistent interpretation, is that what's happening when we make a measurement is that the wave function describes many worlds. When we make a measurement, we discover which of those worlds we belong to. And so that's a kind of many worlds that's implicit in quantum mechanics. And, well, maybe I'll leave it at that and let other people talk. But the second use of the multiverse is much cruder, and it just means that there could be structures, spatial structures, that are very, very far away that we haven't seen yet, where physical laws look quite different. Multiverse has different nuances, but that's, I think, the main idea. This, of course, flies in the face of everything we know about the observed universe, which seems to be uniform and obey the same laws everywhere, and that's a very profound discovery in itself. But there are theoretical reasons to think that if we did persist and wait long enough, we might see different laws acting elsewhere, or that it's fruitful to consider theoretically the possibility that we're only sampling a small part of a much, much larger structure when we sample what we call the universe. So that's the multiverse theory.
Another question from our audience. The questioner asks, if mind and matter merge, then can we alter the state of our experience with disciplined, directed thought, for example, the practice of meditation?
Sure. But I think more effective than meditation is studying physics or mathematics.
A related question from the internet. It says, we talked
Also, you should exercise. It's very good for your brain.
We talked a bit about the geometry that describes the physical aspect of the mind in terms of networking and neurons. This question from the internet is there any geometry that describes the mental space itself?
Yes. Yeah. I mean, there's a whole discipline called neural network theory, which is rapidly developing and very exciting these days, that describes, well, it's too early to say that it really describes how we think, but it describes a rich kind of mental universe that is capable, that allows machines to recognize patterns, to recognize faces, things like this, in absolutely explicit mathematical terms, as the operations of these mathematically defined imaginary objects. There are no real neurons. It's a mathematical construction, so it's geometry in a generalized sense. And the underlying geometry is the geometry of networks and connections between units that I sort of sketched.
Another question from the internet. We've talked a lot about symmetry and perhaps seeing beauty in symmetry. The questioner asks, what about imperfection? Isn't that beauty as well?
If properly done, yes.
It's done perfectly.
No, I should emphasize that symmetry is only one form of beauty, and there are certainly additional forms. In fact, if we look at that fractal, which I think by any standard has a lot of symmetry, I mean, is very beautiful. Its symmetry is quite subtle. You can't turn it some way and get the same structure. You can't. It's certainly not spatially uniform. It's very, very structured. It has a kind of symmetry. If you blow it up, parts of it may look the same as the whole thing. And of course, if you look at any of the classical art objects, they're not perfectly symmetric. Michelangelo's David is not symmetric. So there's a lot more to beauty than symmetry. I mean, well, maybe I should leave it at that. But symmetry is one thing that can lead to beauty.
But just add, if the universe was perfectly symmetric, we wouldn't be here. So it's probably
yes, I mean,
that it's not.
That's right. I'm here and you're there. Therefore, different points in space are different, right? All right.
One more question from our audience for Professor Wilczek. What happens to geometry inside the black hole?
Well, no one knows for sure since no one's been there and done experiments. But the straightforward application of general relativity, which has been tested in other ways, leads to the idea that if you did fall into a black hole, you might not even notice if the black hole was big enough. You would feel some tidal forces as you pass through the surface, but basically nothing is there anymore. It's all been swept into the middle. And you can describe those tidal forces. They get more severe as you get towards the center of the black hole. You get squished into a spaghetti-like shape as you fall into the singularity. So, well, you can describe the geometry in terms of equations, but I think it's better to think about it, it's easier to think about it in terms of how you would sense it if you were moving in this space-time geometry. And that's what would happen. If the black hole is really big, you would hardly notice when you first fell in. In fact, the whole universe might be a black hole and we might be inside it. But nevertheless, you can't send signals to the outside world anymore. That's what's really happened when you fall in. And your fate is sealed. Eventually, you'll fall into the middle. Shortly before that, you'll notice that you're being squeezed into a piece of spaghetti.
One last question from our audience is, does time actually exist, or is it just a measurement of change?
Wow. Well, I think I reject that question. Questions about actual existence are kind of loaded questions. They have more to do with the use of the English language than actual questions. They're the kind of thing Wittgenstein called language games, where so I'd be much more comfortable with concrete questions about phenomena.
Okay, well, I happen to have maybe a last from the internet that relates to time, but is perhaps that kind of question. This questioner, Lauren from Sauk Rapids, asks, if time and space are flexible, is there any possibility that something like time travel is possible, or maybe a faster way to travel through space?
Well, exploiting the flexibility of space-time is actually very limited. You have to use extremely massive objects and concentrate a lot of energy in a small place to get significant bending. So for instance, whereas we use electromagnetic radiation for all kinds of practical purposes of communications and microwave cooking, not to mention sensing the external world, to date, our evidence for gravitational waves, which would be the corresponding effect of bending space-time, are very few and indirect. And very ambitious, difficult experiments are being planned and apparatus constructed to detect gravity waves at all. And the gravity waves they'll detect will be things triggered by violent effects in the universe. So it seems very far-fetched that you'll be able to magnify those kinds of effects in a practical way to speed up space travel or even more drastically to do anything like time travel. There may be fundamental limitations, or there may not be, to the possibility of time travel, but I think as a practical matter, don't hold your breath.
Thank you.
All right.
Thank you all for being patient here. I would just want to remind people as we close this session, we reconvene at 12:45 with music and 1 o'clock with Professor Shear's talk. Have a great lunch.